Section 3.5 Molecular Vibrations. A molecule that contains n atoms has 3 n types of motions. This is because each atom can move in the x, y, or z direction. Therefore, if you have 10 atoms, there are 30 types of motions. Among the 30 types of motions for the molecule that contains 10 atoms, 3 are translational motions. Actually, for all molecules, they all have 3 translational motions. All atoms move in a concerted manner in the x, y, or z direction. Nonlinear molecules have 3 rotational motions. Nonlinear molecules can rotate about the x, y, or z axis. Linear molecules have only 2 rotational motions. This is because the rotation about its molecular axis does not count. None of the atoms move, actually. And then, nonlinear molecules have 3n-6 vibrational motions. So it's 3n in total, minus 3 translation, minus 3 rotation. You have 3n-6. Linear molecules have 3n-5 vibrational motions. All right, or you can say vibrational modes. Therefore, water has 3 vibrational modes, ammonia 6 modes, carbon monoxide 1 vibrational mode, carbon dioxide 3 atoms, so 9 minus 3 minus 2, you have 4 vibrational modes. Benzene is nonlinear, therefore benzene has 30 vibrational modes. So now let's look at water first. I want to show you the translation and rotation of the water molecule. So over here, this T stands for translation. Translation, translation, translation. All atoms in this water molecule move in a concerted manner, or up, or towards the x direction, or towards the y direction. Also, all atoms can move in a concerted manner to finish this rotation about the z-axis, about the x-axis, about the y-axis. So we have 3 translation, 3 rotations. And then the remaining 3 motions are vibrations. You have this so-called symmetrical stretching, asymmetrical stretching, and over here it's called bending. All right. And then how do we determine which vibrational modes does a water molecule have, and what are their symmetries, and why are they useful? Well, briefly, if you can determine the symmetry of the vibrational modes, then you will be able to predict whether those vibrational motions are infrared active or not, if they are Raman active or not. So for example, if the vibrations are A1, B1, or B2 that contains Z, X, and Y, then we say this vibration is infrared active. So in this case, only A2 symmetry is infrared inactive. So sometimes if you make a prediction of a vibrational mode of a molecule, but you cannot find it on the infrared spectrum, usually it's because this is infrared inactive. In this case, if you have a molecule that belongs to this C2V point group and you cannot find a vibrational mode, it's got to be A2 symmetry. If you see those quadratic functions, well, that means those are Raman active. So in this case, actually, if you have a C2V molecule, all vibrational modes are Raman active. So I see, this A1, A2, B1, B2 all contain one or more quadratic functions. Now I want you to again watch this video. This is to determine the vibrational modes of water in 30 minutes and then in 3 minutes. As a review, this is the detail about the vibration of water. You have symmetric stretch. Alright, so this is symmetric stretch. These two bonds are stretched concertedly, and you have anti-symmetric stretch. So when this bond shrinks, this bond stretches. And now you have bending motion. You have this bond order. The bond angle changes. This is CO2. CO2 has 3 atoms, therefore 9 motions. Among the 9 motions, 3 are translations, 2 are rotations. Therefore, we have 4 vibrations. Again, you have symmetric stretch, anti-symmetric stretch, and then over here there are 2 degenerate bending motions. Alright, so 2 degenerate bending. So this band happens on this plane. Alright, this plane. And this band happens on another plane, perpendicular to this computer screen. So this one is the computer screen. This one, this motion occurs in a plane perpendicular to the computer screen. Now let's watch 3 videos. One for ammonia, one for PTCl4, one for acetone. So the point group of ammonia is C3V. This has a D4H point group. Acetone is C2V. So I'll let you watch all 3 videos to get familiar with determining the vibrational modes. Again, why are we interested in the symmetries of the vibrational modes? So 3 more videos. In these 2 videos, I will first determine the point group of formaldehyde. Well, it's just C2V. And then in this video, we will determine which vibrational modes are infrared active, which are Raman active. And same here. This case, this is C2H4 ethylene. This one has a D2H point group. One more example. So in this case, we have a transition metal complex. We have palladium in the center bonded to 2 chlorine ligands and 2 ammonia ligands. And then we have 2 different conformations. We have cis versus trans. In the cis conformation, the 2 chlorine atoms are on the same side. And over here, this is trans, the 2 chlorine atoms are on the opposite sides. So what if you get this molecule, but you don't know whether it's cis or trans? Well, first, they have different point groups. Alright, so first I want you to look at the symmetry elements in here and determine its point group. If you say it's D2H, congratulations, it's D2H. Now again, I'll let you determine this point group. Is this also D2H? It's not. It is not a D2H. This is C2V. So again, this is C2V, this is D2H, but I want you to analyze the symmetry elements in here and also in here. Again, in here you have a C2 axis. You probably can see this axis is C2 axis, and then you have 2 mirror planes, therefore it's just C2V. There are no other symmetry elements other than identity, of course. And over here also you have identity, of course. And then if you say the principal C2 axis is perpendicular to your computer screen, alright, that's your principal. And then you have another C2, one more C2, that give you D2 point group. But in addition, you have sigma H, therefore it's D2H. It's D2H. And also you have element I here, I mean the inversion center I. Alright. So anyway, the point is this: if you take the infrared of this guy versus this guy, you get different absorbance. You have trans versus cis. So it's very important for us to understand that the vibrational modes have different frequencies. We have different conformations. So using infrared, using Raman, helps us to determine the structure of the chemical molecule. Very high symmetry here, tetrahedral, with a order of 24. So 1 plus 8, that's 9, plus 3, that's 12, plus 6, that's 18. 18 plus 6, that's 24. All right, also you can just look at this column. You just square all these numbers and sum it up. So 1 plus 1 plus 4 plus 9 plus 9. So 1 plus 1 plus 4, that's 6. And then 6 plus 9 plus 9, well, you get 24. Actually, you can use this column as well. It's just 1 squared is 1. 1 squared is 1. Negative 1 squared is 1. Sum it up, that's 3. And then don't forget to multiply this 3 by 8. Same here, 1 plus 1 plus 4 plus 1 plus 1. I think you get 8 times 3, that's 24. 1 plus 1 plus 1 plus 1, that's 4. Times 6, that's 24. 1 plus 1 plus 1 plus 1, that's 4. Alright, again, you need to square them, okay? You need to square them. And you get the sum of 4. Times 6, it's 24. Alright? So that's how you get. Okay, now, we have 24 symmetry operations, therefore, a order of 24. But we have only 1, 2, 3, 4, 5. 5 classes. When you have 5 classes, you will have 5 symmetry species. 1, 2, 3, 4, 5. 5 classes, 5 symmetry species. Alright? 5 classes, 5 symmetry species. And again, I mean, if you somehow can determine the vibrational modes of a molecule with a TT point group, and then you can immediately see that only T2 vibrations are infrared active. Alright, any other vibrational modes, you cannot find them on the infrared spectrum. Alright, how about Raman? Well, on the Raman spectrum, you can see A1, E, and T2 vibrations. Alright, so now let's look at some of the vibrational modes. This is A1 vibration. So 1, 1, 1, 1. It's just all symmetric. So this is symmetrical stretching. Alright, so all 4 bonds stretch concertedly in a concerted manner simultaneously. And over here you have T2, T2, T2. These 3 are degenerate. Okay, so these 3 are degenerate. Alright, so in this T2 mode, you have a stretch. Okay, over here that's compress, right? To stretch, to compress. Same here, okay, same here. To compress, to stretch. Same here. These 2 are stretching, these 2 are being compressed. Right, so this is highly symmetrical, and we'll see this kind of cases in transition metal chemistry.